Now, the title of the following presentation is Distributed Co-Simulation Platform and Application for Automotive System Design. And our two speakers will be joining us from thousands of kilometers away, directly from Japan, live and digitally. It is now my honor to introduce the two following speakers to you, ladies and gentlemen, and we will see how soon we can get, oh, here we go. Starting out, we have Taro Shimada, who is Executive Officer, Corporate Senior Vice President, and Chief Digital Officer of Toshiba Corporation. He is responsible for supporting Toshiba's digital transformation and spearheading strategic business creation and promotion ever since April 2019. He was appointed President and CEO of Toshiba Digital Solutions Corporation in April 2020, and Mr. Shimada advised many of Japan's leading global manufacturers on this topic, digitization. He has contributed to the activities of Industry 4.0 in Germany and connected industries in Japan. Welcome, Mr. Shimada. All right, we don't have any sound here in the studio yet, but we're working on that. While we get that fixed out, maybe you can already hear our next speaker. Ladies and gentlemen, no worries, we'll get that working in just a minute. While we wait, I would like to introduce our second speaker of this next slot. Dr. Dai Araki is Chief Specialist working at Toshiba Digital Solutions Corporation. He is responsible for the development of the distributed co-simulation platform and system engineering tools for supporting model-based development of automotive systems. Now, Mr. Shimada, Mr. Araki, and Toshiba Digital Solutions have been a new member of the ProStep IVIP Association for only a few months now, so brand new, and are a major asset, of course, from the Asian region, needless to say, and here we have both of them once more on our screen. As always, our speakers would like to encourage you to ask as many questions as possible, and we will get back to a live Q&A session with them digitally, of course, from Japan right after their feature presentation. So I'm just going to check and see if our sound is working. Gentlemen, would you like to say hello? Good morning.
Hello, can you hear me?
Yes, fantastic. I hear you just fine.
Very good.
Very good. Thank you so much for joining us, and sorry about that, but you know how exciting live is.
Oh, yeah.
Live is always very exciting. So what I would like to do now is actually clear the floor and leave it up to you to begin your presentation, all right?
Okay.
Thank you.
Thank you. So this is Taro Shimada. Thank you very much for the kind introduction. I'm responsible for the digitization in Toshiba. Today, I'd like to explain about our new product called Distributed Co-Simulation Platform. So here's a very quick overview of the Toshiba's organization. I'm responsible for the digital solution business domain also. Directly reporting to Mr. Kurumatani, CEO of the Toshiba. And then there is the Dr. Araki, who will be going to explain about later. Yes. So the first thing that we like to explain about the significance of the model exchange and distribution of the co-simulation platform. So well, you know, with this audience, I don't think I need to explain in a detail, but we need to front loading much more in a design, in a digital simulation way, so that we can do a much more effective job, not because of the COVID-19, but you know, it's kind of the big theme of the system engineering anyway. But at the same time, that this requires the OEM and suppliers working collaboratively, easily and very tightly together. But at the same time, they need to respect their intellectual property. And also that there's a challenge between that there's all kinds of different tools that we use to do the simulation. And then, you know, sometimes it's very difficult to exchange the model itself, or actually that doing a co-simulation is a quite challenge in front of us, I think. So here's the concept of the distributed co-simulation platform. We actually created the distributed co-simulation platform so that the car auto manufacturer doesn't have to directly collecting all the information from the supplier to do the simulation. Instead of that, we actually do this co-simulation over the internet. So this is the basic concept. So that for the supplier, they don't have to provide the model itself to the OEM, but they just connect it, and then the simulation will be done. On top of this, we actually make it a much more platform-like software, so that you can actually simulate a different type of the software all together at the same time. Maybe easier to explain about next slide that I'm showing right now. Like all those softwares we already tested is working, meaning that all those different software co-simulated at the same time. So basically we use the FMI interface to do that, so that in a theory the software which comply with the FMI standards should be able to do the same. Also that we are actively working very closely together for the standardization organization. Here in Japan, METI, Ministry of Economic and Trade Industry, is leading activity of that model-based design working group. And we are working very closely together with the many Japanese companies. And then we are supplying all those technology to be able to do such kind of co-simulation. At the same time that we are happy to join PROSTEP, because this is not only for Japan, this is kind of a universal problem that we have. And we think that we can contribute it to the global supply chains that the people who is really need to do the co-simulation together. So I wonder, this story is too good to be true. Then the people are wondering how, is that really true, and so forth. And the Dr. Araki is going to explain about that in detail, how we solve this problem. So without further ado, Dr. Araki.
Thank you, Mr. Simona. Okay, from now I will explain the detail about the distributed co-simulation platform technology and applications. Today I want to explain the three problems in the model exchanging, and the other hand to show how to solve these three problems. The first one is the portability of the simulation models to exchange over the company or the partner with the teams. The second problem is the confidentiality of the models. And the third topic is how to achieve high performance computations in building the big size co-simulation. Okay. And the first problem is the portability of the simulation model. This is one example of the big level simulation models, which will be developed by the METI MPT working groups for calculating the fuel economy measurement of the vehicles. To making this kind of simulations, the vehicle system designer needed to collect the unit of the model from their partners. For example, the engine controller need to control the transmission controller or some chassis model or powertrain model. This kind of model need to be collected. And the wiring the many signals will require the very significant time and effort for building the whole simulation. And we have a current industrial standard for model exchanging. METI and PROSTEP is defining the guideline and standard styles for model exchanging. The basic concept is designers have their own model, and they write interface definition sheets for attaching the model to handing out to the others. This define sheet is mainly defining the input signal and output signal or some definition or some behavior. And then other side, in the vehicle system level, also the people or SSD people are defining some standard format for design the specification of vehicle level. The main point is that this sheet contains the list of the signals to communicating between the unit. And this is some kind of matrix for who is the transceiver and who is the receiver. That kind of relationships are defined. This is some industrial standard for the model exchange. Our idea is named bus connectors. It's for that this bus connector is the communication unit for each model unit to communicate the signals with the other model unit. The bus connector can be automatically generated from the interface sheets of each model. And from the other side, the CoSimulation controller can several services for making the CoSimulation. The signal communication matrix can be loaded from the CoSimulation controller, and then this controller will be making such service for the signal transactions and connecting the model units with each other. And then also the controller can be making service for the time synchronization to making the synchronous CoSimulation between model units. That is our main idea. So then, when introducing our bus connector approaches, the model unit, and each model unit and bus connector is composing of one model parts for delivering the others. So if we introducing the bus connector approach, the CoSimulation can be become very easy because we don't need to wiring each other models to making the simulations, just collecting the models, and it can be every works will be done in a very plug-and-play style. And these approaches are achieving the high level model portability. The bus connector approach can also solving the second problem, the confidentiality of the models. In case of to hand over the models between the companies, the company needs to care about the concealment of the model. In some cases, this is a very critical issue because the controller model itself has their own intellectual property. So that the company need to care about how to pass the model between companies. When using the bus connector approach, we can make the distributed CoSimulation. So in this case, the company and the design team does not need to handle out their own model to others. So, in this case, we don't need to worry about the concealment of the model. This is the one merit of the bus connector approach. And the bus connector approach is also solving the easily coupling between different tools and or models on the separate locations. The FMI and functional mock-up interface is the standard for exchanging the model. But the typical usage for the XMI is the design team A export their own model into the FM unit and delivering to the other teams. And the team may be importing the 100 models and they making some wiring and connecting their own model and making the CoSimulation. In some cases, we don't need the designer need to care about the cross-tool compatibility. For example, in my case, I eventually experienced some kind of difference in the calculation results that occurred. So that every tool vendors need to heavily care about this kind of compatibility. In our distributed CoSimulation case, we use the FMI standard for implementing the bus connector. So that in our approach is the different tools can be connected by the FM unit of the bus connector. In this case, we don't need to worry about the cross-tool compatibility because each model can be running the execution on the original ones. So we have verified these tools using the tool couplings using the bus connector approach. These are the tools and tool vendors use helping to us confirming this experiment. The potentially I think that all FMI 2.0 compliant tools can be connected with this approach. So now then I'll show you some demonstrations for showing our approaches. The first one is the standard CoSimulations. That is all of the model units for calculating the module fuel economy measurement in one simulator tool. The second case is that we distribute the two parts, and some models are executing on another MATLAB simulator at another PC. The third case is that we are using another tool. In this case, we showed that this case BEOS. Sorry. In the first demonstration, we collecting every model unit in one Simulink tool and starting the simulations. Then this slide, the left side screen is our CoSimulation controller. They will detecting all models are connected and then starting the CoSimulations. In this case, all of the model is collected in the one single Simulink tool and making the CoSimulation for fuel economy measurement. In the second simulation, we are starting the second PC and the second Simulink tools. On the second Simulink tools, we are our powertrain model and the engine controller model here, and then starting the second Simulink tools. Then our CoSimulation controller can detecting the two models are connected on the left side window. And on the middle, we don't need to our powertrain model and the engine control models, so that we deleted the two parts of the model units and starting the simulation. Now then, every model is collected, so that the CoSimulation can be started with, in this case, two MATLAB is running simultaneously. Okay, in the third demonstration, we are starting another tool. In this case, I'll show the BEOS simulators from this test. In BEOS simulator, we are loading our transmission controller model and bus connector of the transmission controllers. And then I'm starting the simulation on the BEOS. Now then, CoSimulation controller can detecting the transmission model, controller model is connected. And we are in the middle of the Simulink tool. We don't need the transmission controller model, so that we delete the model and starting the simulation. So some of the models are connected. And then the second simulation, simulation will be started as another PC. Then all of the models connect. And the starting simulation. So as shown in this simulation, our whole simulation, our bus connector approach is a very high level of the portability of the model, to cutting and the deleting and replacing and the moving the press to simulation. So this is the slide shows some challenges, the solution for the achieving the high performance computation to making the co-simulation. To making that a big level for simulation, we need to choose the right tool and computation platform to run the co-simulation. In the previous simulation, the economy measurement, fuel economy measurement, we need the 2,000 sections real-time driving. The first simulations, and we are making the similar tools on the same machine, so that we have about 300 sections to executing the simulations. But we doing the same simulation on the separate two PCs and with a wired LAN. It takes a longer time. And if we're using some public wires LAN to making the co-simulation, that is it is a very long time to execute. It can be used. So on the other side, we are proposing to using the cloud computing service to this simulation. On the cloud servers, we can using the very high speed networks to connecting the virtual machines, so that we can execute a very high big size simulation in some reasonable speed. So the ideal computing environment for the high performance for simulation is I propose the cloud for simulation. In this case, in these solutions, every design team will have their own virtual machines on the cloud, and the co-simulation can be running within the cloud. This is some practical solutions for making the big size simulation. Okay, let's some concluding remarks. We are sticking new development time to start with the case and copy. So this our presentations will explain the one distributed co-simulation platform to making the virtual design and prototyping across separate design team, supplier, and companies. My pleasure is over. Thank you for listening.
Mr. Shimada, Dr. Araki, thank you so much.
Thank you.
Thank you.
Thank you so much for your presentation, and we have received some viewer questions.
Okay.
All
We're
right.
happy to answer that.
Yes, thank you so much, gentlemen. Then I will take them from the top. The first one is from Eric. These are actually two questions. He says, first of all, thank you for the presentation. And the first question is, can you handle different co-simulation time steps? Meaning some models run with a fixed time step, others with a variable time step at the same time. Is that possible?
Yes, our platform can be handled with different time steps of the models. Our co-simulation controllers have such kind of time synchronization service. This service also handling the different time steps of the running on the models.
Thank you, Dr. Araki. The second question, also from Eric, is how do you differentiate your tool from industrialized tools like AVL Model Connect?
Okay. In every case, from my understandings, the every tool is currently the standard CoSimulation tools. That means the many modules can be collecting in the one simulation environment and running. That is the approach. Our approaches can handle with both standard CoSimulation approach and the distributed CoSimulation approaches. The two cases that is very depending on the actual use case. We can select both approaches.
Thank you, Dr. Thank you, Dr. Araki. I hope that answers your question, Eric, and thank you for asking that. Moving along from Reiner, gentlemen, we have the following question. How important do you see explicit traceability linking between the individual simulation models as part of your FMI plant controller CoSimulation setup? For example, for functional safety, which is a hot subject here in Europe. Gentlemen, what is your take?
Yeah. So I cannot catch the point of the questions, but maybe the CoSimulation is a very practical for solving such kind of functional verifications. For example, in case of the unit testing, so that they don't need to care about the other parts. So that this kind of the CoSimulation will be a practical approach for the making functional safety. I'm sorry. That's the mind.
Yeah.
Thank you. Thank you so much, gentlemen. I have one last question before we close for this slot. Which simulation, Marvin asks, which simulation model types can you co-simulate? Are you limited to logical simulations, or can you model multi-body simulations, computational fluid dynamics, etc. as well?
Okay, so basically our platform is supporting the FMI as the standard for the model engine. So that this platform is some limitation for to the also same limitation with the FMI. So FMI basically we need to develop the more advanced features for the FMI standard.
Well, I guess that the easy answer would be that if the simulator has FMI integration, it should be work.
Right.
So if that is given, then it should work. Thank you. Thank you, gentlemen. Thank you, Mr. Shimada. Thank you, Dr. Araki, for joining us. Thank you for your wonderful contribution. And we look forward to seeing you next year.
Oh, yeah.
Okay.
That would be nice.
Hopefully in person. Greetings to Japan.
Thank you.
Thank you.
Thank you so much. Take care, gentlemen.
Bye.